All right, our second speaker this morning is Guido from Parma, and he will tell us about rollercoaster cosmology and gravity-based factors. Please go ahead. He will get the video on the 45 minutes. No, go ahead.
Okay, hello. So I'm going to talk about these papers done in collaboration with Nemanja and Alex Westphal. So in these papers, we try to actually take seriously some idea that was already there, which is that inflation does not really need to happen in one single long period. So let me start by reminding you that inflation was invented to explain the universe naturally. So, you know, now what we were calling cosmological naturalness now translates into the problem of naturalness of the effective theory of inflation. Now, in semi-classical gravity, we usually take a derivative couple. Inflaton and the potential is kind of sheet symmetric, but then when you think about quantum gravity, the idea is that the global sheet symmetry does not really survive. People expect the field ranges to be short. And also, well, there is, you know, the idea that there is too much tensor power. So a possible answer is the monodromy to answer the problem of global symmetries, and also roller coaster idea, which is the fact that field ranges can actually be shorter than you expect. So in usual slow roll inflation, for instance, the phi square inflation, basically the phase space that starts inflation is just a sliver for field ranges actually larger than M Planck, okay? And to have enough inflation, you should actually start here, much larger than M Planck, about 10. So basically, the idea is that inflation occurs at large field waves, and it's not sure how much to trust the arguments beyond the Planck scale. And then a solution for large field inflation can be the monodromy idea. So monodromy in Greek means running around singly, and the idea is that you can actually get an effective large field excursion in a small compact field space, such that theory is under control. And in fact, you all know a simplest physical realization, which are Landau levels. So it's a quantum magnetic particle in a magnetic field, and in 4 dimension you can think of having like an axion that's coupled to a 4 form. So effectively you get a massive axion with an additional flux quantum number that actually raises your effective cosmological constant, and so it gives you long inflation in a small field space. So now the problem is that yeah, monodromy works very well for a large field ranges, for large fields, and what happens is that usually large field models are excluded by data. This is an additional worry. In fact, the latest BICEP results tell you that R is less than 0.036, so we are in this small potato, and you know, all the power law are basically excluded. Notice that here, of course, to exclude a power law, to exclude any models of inflation, you have to tell me where on the potential the field is when the perturbative modes that you probe are produced, and usually it's taken we illustrate the range between E equals 50 and E equals 60 before the supposedly end of inflation, meaning when if inflation ends if it's only a single period. Okay, so now the idea is that we want to relax both the theoretical worries and the data issues. So by shortening the field variation, we also can get a redder spectrum and a small R. Now, a key insight is that observationally, we do not need 6 E-fold in one go. So we only actually probe in CMB, and so far in large-scale structure, the first 10-15 E-folds of inflationary expansion. And then, in fact, the accelerated expansion may stop and go and happen at subsequent lower energy scales. So this looks like a tuning of a few parameters, which is not really atypical of inflation. And basically, the interesting thing is that CMB constraints on a given, model, so potential, will be modified, and for the future, very interesting predictions for short-scale experiments have to be figured out, because now we will have many, astronomical observations in the next decades, to start with gravitational waves at high frequencies that can help us, in fact, test the longevity of inflation. Right? We would like to go beyond the first 10, 15 years. Okay, so in a sense, what I'm saying is that log smooth inflation is like the desert in particle physics. So in your effective theory, you basically have H, and then you have some light fields, and then at some point at TeV, well, GeV, hundreds of GeV, you get the standard model plus other light stuff. So what is around here? I mean, all BSM theories assume that there is something, and maybe we can test. We can see if this something also is a more complicated inflaton sector. Okay, so let me start by briefly telling you that even in this roller coaster, we solve the usual horizon and curvature problem. So let me just start with the toy model, which is a simplest architecture. So you basically, this tau is conformal time, and n is the number of E-folds. So basically, what happens is that we get inflationary expansion, and then radiation domination periods that are in between. And in this kind of simple example, let's try to look at the horizon problem. So basically, the horizon problem is that in normal matter, basically the length with respect to the horizon, the length, like any length scale, goes down. Whereas, and so at some point you get out. You are looking at the scales that were out of causal contact in the past. Okay, so this is the horizon problem. Now, with inflation solves it because during inflation, this ratio stays constant. And so basically, the whole universe was actually born out of a small region that was in causal contact in the past. Okay, so this is the way that standard inflation solves the horizon problem. And basically, with the roller coaster, you just intersperse, these constant ratio periods with periods where you are a bit out of causal contact, and so in the end, basically, you get this condition, which is that you need our universe to be originally, so our scales have to be larger than the horizon originally by the initial length scales times the final Hubble. So basically, sorry, there's a slide missing. Anyway, yeah, there was a slide. There is a slide missing that shows you the evolution of the inverse horizon with respect to the E4 number. Okay, so let me then go to the curvature where I see that there is the figure. So basically, what is the curvature problem? The curvature problem is why the universe is basically so homogeneous today, and why basically the curvature in the beginning was so small, because if it were slightly larger, the universe would have recollapsed in a Planck time. So basically, what inflation does, takes a small region and then expands it, and on the surface of a sphere, if the sphere is very, very big, you basically feel like you are in flat space. So the curvature problem also, with normal matter, of course, the curvature scales in this way. So given the ratio at two different times, the curvature goes down, and instead during inflation it's exponentially suppressed, and in roller coaster, sorry, here I said so it goes up. So during inflation, basically you get this exponential times a factor that you have to keep under control in this way. So basically, the curvature during inflation goes down, but then in these radiation domination periods, it goes up again, then it goes down, then it goes up again, then it goes down. And the black line is what would happen in a long uninterrupted inflation. So basically, as long as you keep the total amount of time that you spend not in inflation, then the curvature problem is fine. And in fact, in roller coaster, you kind of expect the curvature to be largish, and maybe this is one of observational handles that we have, right? I mean, if we were able to see curvature in the next few years, then long smooth inflation would be less stable. Okay, so let me go to perturbations. So perturbations so far have been calculated for tensors, because tensors only depend on metric, and here in this simplest example, we just make assumptions about the metric, right? I mean, de Sitter, radiation domination, de Sitter. So scalar perturbations instead are a dynamical input, since GR has no scalar mode. So this is more model dependent. Okay. Now, when we have multiple stages, we expect to have multiple fields, and therefore we need to have little hierarchies. I will show you later an explicit example of this little hierarchy. Okay, so what we are looking for is the approximate scale invariance of the theory for long enough, even piecemeal. And how do we calculate perturbations? Well, let me take as a prototype the Starobinsky model, okay, which was in fact the original one that Mukhanov and Chibisov calculated. And this is a scale invariant model completely. However, any solution of this model breaks conformal symmetry spontaneously. And so we have a Goldstone scalar, okay? And the cosmological constant, which is an effective cosmological constant, is an integration constant, okay? So then basically you can see inflation as a spontaneous symmetry breaking of time translation, which it is, and the fluctuating mode is buried or fed to, I mean, depending on the way that you see it, in which gauge you see it, to the curvature term, okay? And therefore, once you understand the physics of where the fluctuations come from, it's easy to calculate. You just take this scalar field mode, you quantize and compute the two-point function. So in general, you have a harmonic oscillator with time-dependent mass, which is this z dot over z, and for a scalar field, this is model dependent, but in the simplest example, I mean, which is what we consider for tensor, this depends just on the metric, okay? And so, at the end of the day, when you write down the equation, it's actually cute because you find out a Schrödinger equation for the mode with anti-tunneling boundary condition, because of course now you are solving a problem in time and not, in space as we are used to in standard quantum mechanics courses. So here is how the barrier structure looks like in, de Sitter radiation nomination de Sitter, okay, as a function of tau. So radiation nomination we actually picked because this potential is actually zero, and this is it's particularly simple, okay. And here it's basically 1 over tau squared. So yeah, this is the Cosmologia con quattro stagioni. So as you can see, there is like initial inflation where the inverse co-moving Hubble decreases, then there is a radiation nomination, then another period of inflation, and then finally you get into our own universe, and the corresponding band structure is for the potential barrier structure is here. So these are scales that we consider. These are length scales that we consider. So this is basically a length, and this is an inverse length. And so when you compute the mode function with respect to the standard, well, no, this is just the mode function. Basically, for each of these colored lines, you find a different behavior according to the fact that it went above or below or in the middle of the barriers. Okay, so you have a mode which is on very, very short scales. So basically, it does nothing. So this is just, the normal fluctuations of a free scalar field that you subtract. And then you have modes at different scales. So, for instance, the one that is on very, very large scales, it doesn't oscillate, and then at some point it freezes to a constant. And when you put them all together as a function of k, and you take the limit towards the end of inflation, this is what happens when you divide by the usual de Sitter 1 over k cube power spectrum. So this is, in a sense, some sort of form factor for the power spectrum. Okay, so the power spectrum is the one of inflation for a while, and then at some point it drops. Then it oscillates, and this oscillation is nothing but Gibbs phenomenon, because we take no smooth transition between de Sitter and radiation domination, and then it goes flat for a while. By flat, I mean really de Sitter-like, 1 over k cube. Then it goes down, and then it ends. And so this is what you would get for the mode that just for the tensor modes that just depend on the metric. Okay, if you have a scalar, then you can have some more interesting behavior in during the transition. So you may have some sudden transition that excites you, and so the power spectrum need not necessarily to decay so much, okay, or can even spike. So, in a sense, and notice that this was done before the latest bicep result, okay, power law inflation can be viable again. Of course, we assume that the potential is somewhat flattened, so of course it's not phi square, but for instance, you can get the square root potential that falls into the potato if the first leg of inflation, the one that corresponds to the one for which in the beginning the CMB modes were generated, now it's like 40 inflows from the end. And then there is another 15 inflows after that is at lower scale, and it helps you solve the horizon curvature mode. And then, the correspondence, the usual correspondence between CMB prediction and length of inflation is modified. And therefore, we can make these models viable again. Now, of course, this is extremely outdated, well, by just one data release, and tells you that you really, really need to get the potential much flatter, okay? So let me now switch to a more explicit model in which we have 2 stages of monodromy inflation that are separated by matter domination when the first ends. So basically, this is some sort of hybrid looking model in which you first inflate along this direction, then the oscillations here are effectively a couple of wiffles in principle of matter domination, and then you inflate along the orthogonal direction. And basically in this model, as you can see, we have power law, the powers that are, just some parameters that allow for inflation. And then you get these mass scales, okay? So the roller coaster or double coaster requires you to set a small hierarchy between the m, the full scale of the potential 1 and 2, and then you have to require that, of course, these mass parameters are of order a tenth of m1, okay? By the way, yeah, here, of course, I'm taking these m1 and m2 to be of order m Planck. Okay, so given this model, what are the CMB predictions? Yes.
Much smaller than m1?
Yeah, it can also be much smaller.
Constraints in this ratio?
No, not really. As long as you respected the EFT, I mean, and of course the length of inflation allowed, then it's fine. I mean, you just have to, in this particular model, you have to make sure that the first leg of inflation lasts like 15 e-folds, because we don't have evidence in the CMB that it's interrupted, okay? And then, so this is one constraint, and then the other constraint is that, the total one is about, 55, 60 equal. And then, of course, the theoretical constraints that we don't want, parameters to go outside of the ESP validity.
You have a long period of radiation
in between, yes. Now, in this particular model, no, we like it's just matter because we just assume these and solve for this potential. But in principle, yes, we could.
I mean, you can imagine very efficient reheating at the end.
Yeah,
so
and
it's
then
possible to imagine this. Of course, it might mess things up some way with the continuation of the. But
let's say M1 is the usual 10 to the 16 GeV and M2 is negative.
yes.
Would it be viable as two stages? I'm not 100% sure. It might
be.
There are you need to be very careful with matching the conditions, but there are I don't know if the people think it, but there are papers that tell you how to pick these fields. So.
Yeah. So in fact, I mean, if you hear,
how long is the last stage?
Yeah.
If it's short, then no problem. But
right.
It's very long, then.
Right. Yeah, so for instance, suppose that this first stage is 30 and then I don't go here, but I just reheat. Then, something happens and then I go down in energy. And then, yes, you can imagine things like that. Yes, okay, so now, I mean, for definiteness, I am considering this, and so this is how the CMB predictions now go. Now this, the number of e-folds is an additional parameter that can vary. And, this shifts your prediction to the red as an e-fold goes down. And, varying from 0.01 mu to 1, of course, as a ratio of m Planck, it goes up, and of course the powers brings you at very high tensor level. Okay, so what do we do? Well, here actually we can also recognize that whenever we have a monodromy inflation, the standard kinetic term that I wrote you in the beginning is not necessarily the correct one, because you can think of it as an actual effective theory. Okay, so in particular, you can do write down the operators that are allowed by the four-form gauge symmetries. Or you can write down all the operators and organize the expansion by methods of naive dimensional analysis, as you do for heavy quarks effective theory. In particular, this Q, so the number of flux parameters, has to be counted by 1 over m, and then there is the 4 pi from the loops. So the field is counted by m over 4 pi. The derivatives and the masses are suppressed by m, and then the number of fluxes by gauge symmetry, since basically it's proportional to m times phi. There are 2 powers of m at the denominator, 1 power of 4 pi, the overall normalization is the usual one, and then you restore combinatorial factors. So in the end, in a paper from some years ago, we realized that by writing down all the possible operators, you are within your effective theory, and all these operators can formally resum to what is known as K inflation. Okay, so basically you can have a bunch of kinetic terms. So you can have a generic Lagrangian that depends on the field and on the d phi square, with a potential that's typically flatter, okay, than the usual one. So to summarize, physically, when you consider higher derivative operators, you get smaller R, okay, and so you get flattening. So, however, flattening meaning you go into the stronger coupling regime, and therefore you expect non-Gaussianities, okay? So the data tell you that non-Gaussianities cannot be much larger than order 10. This means that the coupling in inflation cannot be too strong, as we all know. And the problem is that now you correlate R with the non-Gaussianity. So if you get stronger coupling, you get a smaller R, tensor to scalar ratio. But then you get a larger non-Gaussianity. So what happens to R in strong coupling is basically going from, so here I illustrate you 2 models. So one model is when we add an x cube over n to the 8, which is inspired by some string construction, and this is the usual dBi action, okay? So you can see in the RNS plane how these triangles move when you add the additional kinetic term, okay? So you do get lower R, and you get slightly redder in this polynomial case, and in dBi instead you get around because of the more complicated functional form. Notice that actually here we are assuming the potential parameters to be fixed and the number of e-folds to be fixed. So this is why also we get this more complicated movement in this NSR parameter space, because NS and R are observational parameters that depend in a non-trivial way on the potential parameters and E.
About 10 minutes.
Yes. So basically, as you can see, this NG versus R in the polynomial case does not give you strong constraints, because this polynomial case basically gives you a speed of sound that has a lower bound, and therefore the coupling, and therefore the non-Gaussianities cannot be too strong. However, for DBI, actually, if you want low R, you do get largish FNL, and therefore this might be something to look for, in the data, especially, in 10 years. We should be able to completely rule out or detect these kind of strong coupling monodromy models. Notice that for fun, so this is something that we took from Lightberg collaboration, forecasts, and this is the expected constraint if you do not find a signal. But then for fun, since the actual data are 1 sigma away, more than 1 sigma away from 0, this is what we would get in this NSR plane if, this is what we find in the sky, okay? So, in 10 years, we will have beautiful data that for sure will tell us whether what I told you until now makes sense experimentally. Now, a very interesting thing that's, I hope, just the first of many other small-scale predictions is the generation of high-frequency gravitational waves. So what happens here? So from string theory constructions, since we are dealing with the 4 forms, okay, it is totally natural to expect the coupling to other gauge fields, okay, so higher order forms. And when you dimensionally reduce, in particular, what you get is usually something like the axion coupling to a dark Q1 through an FF dual E dot B coupling, okay? Now, this kind of coupling has been studied a lot in the literature, and, the coupled axion gauge field system has, obeys these equations. Now, these equations have one interesting feature, that there is a tachyonic dependence of one helicity for fast field, okay? So, fast field means that, of course, gauge field is generated because this operator is actually a total derivative if F1 is a constant. Therefore, it has to involve a derivative of the axion field. It depends on the speed of the axion field in these units. And notice that because of the plus or minus sign, one helicity will always be tachyonic, okay? So this means that you can efficiently generate a gauge field background, okay? Now, the full solution is complicated. So, for instance, here I show the solution when you start from 0 field, there is an exponential growth, and then this is the total energy over m Planck to the 4th in the gauge field. At some point you have to stop, okay? Because the exponentials are never physical all the way, because at least for energy conservation, right? So you do expect a saturation. However, it has been shown also numerically that we can actually trust this simplified solution up to end of inflation, right? And where by end of inflation, I mean when the back reaction of this field starts to be important, and so at some point you say, I stop here, and my inflation ends there, and so my background changes. So what are the observable? Now, the observable is that at small scale, you have large non-Gaussian perturbations, and you get gravitational waves. So gravitational waves, you expect they to be generically chiral, okay? So only one polarization is generated, and they take this form. So basically, you know, the one comes just from, you know, the usual de Sitter production. And then you get the additional generation that, of course, depends very sensitively on this psi parameter, which is the speed of the scalar, of the axion. And where should you compute these? Well, you, of course, you should compute these at some e-folds after you know, the CMB perturbations are generated. So in particular, in our potential, you generate CMB perturbations here, and then at some point the field speeds up. And when it speeds up, then it generates gravitational waves, okay? So now this length in e-folds will give you a correlation between the CMB prediction and the frequency of the gravitational waves that are produced, okay? And so this is, in fact, the formula that relates the frequency with respect to the, you know, number of e-folds where you compute your CMB prediction, and well, this is just a pivot scale for you know, the CMB. So yeah, no. So this, in fact, is what you can observe. Okay, so this is now as a function of the frequency, which corresponds to the number of e-folds, the generation of the gravitational waves as a function of a fixed CMB, e-fold CMB. So here I'm assuming the first stage lasts 35 minutes, okay? So this in particular gives me a very specific prediction for NX and R. And as a function of the coupling to gauge fields, I get a different amount of gravitational waves that I can see at different frequencies. Here I show LISA sensitivity and Big Bang observer sensitivity, okay? Then, by changing instead the number of e-folds where CMB perturbations are produced, here fixing F, basically we can get loud signals for different experiments. So for instance, here I show you LISA, Big Bang observer, Einstein telescope, okay? So, you know, if this scenario or, you know, something equivalent is operational in our own universe, we have a very loud signal that we should really be looking forward to see in, you know, the different instruments in the next decade or so. So now, as a last slide, let me also tell you something that's curious, and it's been appreciated recently, that whenever we show the prediction of CMB, or the predictions for the constraints on inflation from CMB analysis, we are always assuming also normal evolution for the late universe when the actual astronomical observations are made. In particular, if you take seriously this H0 controversy, that means the discrepancy between the Planck inferred value of Hubble parameter and the supernovae the supernovae direct cosmic distance ladder, then there are models that aim to soften the tension, and one of these models is the so-called new early dark energy. But I mean, here I show just because it's a studied model, and you can actually make the analysis because it's a definite model. But this feature is actually common to several other ways of resolving the tension. So it turns out that in this kind of models, the NS that you would infer from the data given this model is much higher than in normal lambda CDM all the way. And here, for instance, I show that the prediction of the usual Starobisky model are totally off, whereas, for instance, you would get, you would get more favored instead a long inflation with a power that gives you almost blue, well, not yet blue, but almost a blue spectrum. Okay, so the conclusions are now. First of all, I try to convince you that it's not really obvious that inflation should happen all in one go. Okay, and interrupting it, which was the original motivation, in fact, was can help you with naturalness, and in particular, it helps fitting data for large field models. Now, horizon and curvature problems are not a problem; they are easily solved. You just need to sum up the number of equals until you completely end inflating to be 55, 60 more than the sum of equals that you didn't spend inflating up until that point. Now, interestingly, when you allow for these possibilities, model building reopens. And one very, very cool thing is that you get one interruption, even just one interruption. It's very predictive because then it can give you correlated signals at large and small scales, which so far we never really look for, right? I mean, we just say, okay, CMB predicts this, and then at small scales I have this, okay? So it's we never really look for this kind of correlations, okay? But these kind of correlations are what could tell us more about inflation. Now, the question is, what are other interesting observables? So one symbolistic example is, having, for instance, a very loud gravitational wave signal for, the next decade experiments. So, for that, and we are thinking about other possibilities.
Questions to Guido? Yes.
Guido, in this case where you have multiple stages, so we have basically additional light figures.
Yeah.
You have isocurvature variations also.
So, in principle, you can expect them, but you know, as a curvature perturbation can be cancelled, you know, in the subsequent radiation phase. So you can expect them for sure. You can expect curvatons, for instance, or you can expect the transition, you know, to produce you local non-Gaussianity and the curvature perturbation. But of course, this is all model dependent. Yeah. Yes.
So about the gravitational wave signal.
Yes.
So can you recap a bit the difference, because already Donkey et al. They already have big signal, right? Now that's the first stage of the inflation.
Right. Yes. Yeah. No. In fact, you are saying just the usual. So yeah, the fact that it's a loud signal. In fact, we just in fact I even cited them. Like, I mean, they did a numerical analysis. So what's new here is the fact that the frequency, of course, can change and can be, because usually people think of these as happening at the end of 60 defaults of inflation. Okay, now at the end of 60 defaults of inflation, it means that it's on extremely small scales. Okay, so here instead, I'm telling you that it can happen much earlier, and also that you know, if the model is simple enough that you know it happens, for instance, at the first stage, then these will correlate with the CMB, you know, predictions, right?
Yes.
Can I ask you some more details about this? Because so if my understanding, just to check that my understanding is correct. So what happens is that by a second stage of inflation,
Yeah.
you are able to shift the signal towards smaller frequencies, right?
Yes.
If we didn't have any second stage of inflation, this would happen towards the end of inflation, so it would be a crazy high frequency.
Right, exactly.
But then it is not clear to me whether this should really affect the duration, because you have back reaction of gauge fields, right?
Yes.
And so would this affect the actual duration of the second stage of inflation? If you didn't have gauge fields, okay, you suppose you switched decoupling to gauge fields off, and let's say that you have delta n for your second field, second stage of inflation. Now, would this delta n, which is what actually helps you make predictions on the frequency of this rise in omega GW, would that change if you had the correct tools to take into account this back reaction?
So, no, I understand. Actually, I think that so this frequency is determined by the length of the first stage. So this happens at the end of the first stage of inflation. So let me go to the potential. So here I start inflating, here I generate CMB perturbations. Then at the end, you know, the field just starts speeding up.
So you produce gauge fields, and just because
here, exactly, I produce the thing. And so the frequency is determined by this length in field space, which translates into, you know, NK frequency.
But isn't that in the standard scenario that you can?
Yes,
I mean,
but the standard scenario, no, but then the standard scenario assumes that these must be at least like 55 to solve the horizon problem. Instead, we are saying, I mean, these can be short. Okay,
That I get.
then I just need another stage to inflate enough to kill curvature horizon and so on. So now you are asking, is the presence of, I mean, does the presence of gauge field, you know, modify this? Well, Yeah, maybe, but I mean, this is another sector, okay? So at some point, then I get these gauge fields that give me a radiation domination period, then it lasts for a while, and then at some point, I have an effective cosmological constant given by this second field. And then, you know, this.
Let me try to help with the explanation. See, remember that you're making these, you know, U1s near the end of a stage of inflation because of the fact that they're produced by an operator which would be a total derivative and would be coupled. So if phi dot is small, when you're way up on the slope, you're not, you know, making these U1s almost at all. Okay, because the coupling is too weak. So you don't have much of that back reaction and so on and so forth. Okay. You start turning them on real hard, okay, near the very end when the field is, you know, sort of going down and wiggling around and so on. Is there some sloppiness in the estimate where this happens in terms of the frequency? Yes, of order of 1. Okay. Yeah. In terms of that, you know, because in this calculation that we've done and so on, we were a bit, you know, there is probably a more precise improvement that would be required to precisely determine the frequency. That will take into account the back reaction contributions, but that's basically telling you that that's order 1 in the default.
Okay, so essentially it's not possible to say that it happens at Lisa and instead it happens at SKA or something.
Oh,
it happens likely on the left.
Unless you see, it's possible to say that if you have multiple stages.
Yes.
Okay.
But you would need one stage, one interruption at every stage.
Okay.
Now, obviously, we can't predict that. The idea is you go and you look in the sky.
Yeah.
And now you start seeing these strange, you know, chiral gravity waves at the scale of Ska, at the scale of Lisa, at the scale of, I don't know, Virgo. And then you say, oh, what's this?
Yeah.
Okay. And then you say, maybe you have interruptions, several interruptions during inflation, and at each interruption you generate. Yeah. If, of course, you had the axion that coupled to a U1 of a certain kind. Is it possible? I don't know. Is it guaranteed? I don't know. Is it possible? Yes. Because, you know, in these supergravity models, etc., that you inherit from string theory, in principle, they tell you, okay, think of axillars, okay? You have many axions at different mass scales. You have, in principle, many different U1s. So if you get lucky and all of them get turned on, maybe you get something. Okay. But there is no guarantee on it.
All right, I think it's time for lunch, so let's thank Guido again.